In his late years, when he was even 67, he generates papers 1 per week. 1 article per week, 1 mathematical article per week. Let's talk about Laplace, the main tool for continuous time systems. So what I want to do is talk a little bit about the history, this interesting story behind it, and then talk about the big picture in terms of system modeling, how we utilize Laplace. Then work on some of the definitions and properties that we care about. All right. Laplace is a really powerful tool to solve a lot of ordinary differential equations, ODEs. And Laplace, this is a brilliant scientist, mathematician, and also physicist. So he worked on a lot of problems. He was born in the 17th century, so Newton became quite a few years later than Newton, but he was valued as the Newton in France. He studied a lot of problems with someone that you also know from your other mechanical engineering classes, Lagrange. Modeling is a main part. Lagrange contributed a lot to modeling. Lagrange opened a new page for doing models of complex systems. And both of these, Laplace mainly. So Laplace is actually a student of John D'Alembert. He is another very brilliant scientist and mathematician. You may know something from the ordinary differential equation. So whenever you solve an ordinary differential equation, you need to find the roots of the characteristic equation. The most important assumption for that is that if you have an nth order ordinary differential equation, how many roots do you have? N roots, right? That's the fundamental theorem of algebra. Nth order polynomial, nth order, n roots. They may be repeated, but you can have n roots. So that's from D'Alembert. So it's actually known as D'Alembert-Gauss theory. So another good name here. It's an interesting story. D'Alembert first published an article to prove this fundamental theorem of algebra. And it was well received. And then later, Gauss looked at it. Gauss found some typo or error in the proof. So then he both him, and then together they were named, the co-inventor. They were regarded as co-inventing the fundamental theorem of algebra. So we're going to talk about Lagrange actually later today as well. It's another story. All right, so the big picture related to control system analysis is that we can work on ordinary differential equations and then find the solutions, finding the poles and figuring out the coefficients for different modes, right? But all you would remember, some of these are very tedious and cumbersome to do. And it's difficult sometimes to use a computer to do that, at least in the early days. Now, Laplace, he transformed the problem into a different domain. So you apply Laplace on ODEs, and then you get, now you know, the transfer functions. These are algebraic equations that, after some manipulation, then you can go back to the time domain. In the Laplace domain, it turns out many of the complexities in ODE, especially in control system analysis, becomes extremely easy. And the biggest advantage, as we will show, is convolution. Now, some terminologies, just to set the pace, set the language, as set a common background. We say a set, such as 1, 2, 3 here, is a defined collection of distinct objects. All right? So the set 1, 2, 3, 5, 6, the set of integers, we call it Z. So Z set is the set of integers that we use. Positive, just integers. If we go a little bit more than integers, we use R to denote the set of real numbers. So 1.5, 1.2, 1.3, pi, e. These are belonging to the set of real numbers. So we use the notation belongs to, such as this, to say this is an element of this set. And then from integer to real numbers, to go a little bit even more beyond, is the set of complex numbers, 1.3 plus j times 3. Then a complex number, so this is belong to the set C over here. We use a little plus sign at the right border of the set to denote this is a set of positive numbers. So if it's R, this is R plus is the set of positive real numbers. If it's C plus is the set of positive integers. And then triangle equal to say defined as. So if I say yt equals to 3x plus 1, t is a function of time, then y is defined to be 3 times x. All right. So as another recap, continuous time functions in this class, we're going to be focusing on functions that start with positive index of time. So we denote this function f, whose input is time t, so the domain of f is time. Then we use this notation. F, it maps some number, some time in this set R plus. So this is positive time. We map it to some other number in the set of real numbers. So this is a function, this is a definition of function of time in this class. This is a formal notation. F is defined from mapping from the domain R plus to R. And usually, unless we specify other words, when we write ft, we say it's a continuous time function. All right? This index here, R plus, means that anything with negative time index, we treat it as 0. Just with the convention. All right. With these set up, let's recap and review the definition of Laplace transform. So the Laplace transform is defined over the continuous time function that we defined over the last page, in the last page. It transforms a time function to S domain, so a different domain. The index here is t, and then in the Laplace domain, it's S. It integrates out time by this integration. It's integration of the entire domain of the function f from 0 to infinity, and then find this special exponential term, e negative st dt. T is going to be integrated out, and the entire function is going to be a function of s. So that's the definition of Laplace that you guys learned. Whenever we think about a definition, it's worthwhile to ask a question. If we think about the integration doesn't always exist. The integration can be, if I want to do integration of this one, then it's the area. So if I want to do the integration of this function, let's do this g here. G is a function of time. We want to integrate gt here from 0 to infinity. You can write it any way you want, but this integration doesn't go to some fixed terms, right? This is going to infinity. We are doing the evaluation of the area, and then this area just continues to grow. That's why when we actually look at this integration, there are underlying assumptions for the function ft to satisfy for the Laplace transform to converge. It turns out if the function f of t, okay, it can have jumps, it can be discontinuous, but if it's piecewise continuous, so you see sections of continuous functions together, then it's going to be good for this integral. So the integral, Laplace integral, is pretty thorough in terms of function properties. You don't have to be perfectly continuous, but as long as you're piecewise continuous plus another condition that we're going to talk about now, you're going to have convergent Laplace transform. And that second sufficient condition is this. So the second sufficient condition is that your function can go to infinity, actually. So f of t, it can go all the way to infinity, no problem. Laplace will give you a convergent Laplace transform. As long as you don't go too fast. As long as I can somehow create an exponential function that will go faster than you when time is sufficiently long. All right? Mathematically, this is what it says. As long as this function f of t is lower bounded, so this is smaller than this curve, than this exponential curve. As long as the function is lower bounded by something that exponentially grows, you can go to infinity. But if I can surpass you and bound you, then there will be no problem. That's the second sufficient condition.
Hello, sorry, Professor. Can you pause for a moment?
Okay. I think we're back on audio again. Let's take a look at the graph and take a look at the definition again to see why this sort of makes sense. So I want to give you guys some insights of why I can allow the function of ft to go to infinity, but still have a convergent integral. If I take a look at the Laplace transform definition, you guys already know that if some function that does this, if I just want to integrate this function, it doesn't work. I'm not going to be convergent. Now, what do you think is making this whole thing work? The integral is going to convergent, even if f goes to infinity. As time goes to infinity, you have this term a little over here that can scale your function effectively. So what actually happens is that this is doing something sort of like this, just an illustration. But it's going to make the entire multiplied term eventually to go away. That's the key for the integral to be convergent. We're going to see something similar again in the discrete time domain. Good that you guys have some. Oops. As we wait a little bit, let's think about some examples that we see all the time in control systems. The most important is this one. As long as you get this relationship loud and clear in your mind, then most of the terms, most of the other functions of time can be figured out pretty quickly. So this is the most important, I would say, Laplace transform pair for control systems. If you have a exponential function, then the Laplace transform is 1 over s plus a. No matter what kind of a it is, your function ft, it can grow exponentially to 0, or it can grow exponentially to infinity. The Laplace transform is this guy. It obviously satisfies the conditions that we talked about. First, it is continuous. It's not even piecewise continuous. It's better than piecewise continuous. And then I can bound this function by some exponential function, right? I can easily do this. I can bound it, upper bound it. So I know it's going to have a Laplace transform. And then from there, we can use we can do the integral and then derive this. So I'm going to do this once together. So f of s, the Laplace transform, is going to be integration from 0 to infinity, the function itself, e negative 8t times e negative st, and then over time. The most important property that we use is exponential functions are amazingly fantastic in the way that if you put derivative on exponential function, you still get an exponential function. If you have, let's combine this a little bit, e negative a plus st, this is nothing but derivative of e negative a plus st and then negative a plus s. So this is chain rule. The derivative of e negative ast is e negative ast times the scaling factor in front of t. This is, so that's why I have to divide by negative a plus s. Then this term is not a function of time, so I take it out, negative 1 a plus s, and then it's just going to be e negative a plus st with t evaluated from 0 to infinity. This is easy enough. We get e negative a plus s infinity minus e negative 0. So it's essentially e 0. Exponential function power to 0 is 1. And then this exponential function powered to e some huge numbers is going to give me 0. I have a negative 1 here and then another negative 1 here. They're going to produce a positive 1, and then in the denominator is s plus a. It's worthwhile to do a little bit of exercise from time to time to be able to get more familiar and hands-on practice on these. I repeat again, exponential function Laplace transform is 1 over s plus a. A first order exponential function is 1 over s plus a. That gives us the fantastic time and opportunity to look at this one. This is not an exponential function. This is a step function. But we can quickly say the Laplace transform is 1 over s, because this is essentially, this is because you just let e negative at with a equal to 0. So this is still a function of time, so I put the time index. So this is a function of time. 1, this step function is a function of time, but with exponential functions, the scaling factor to be 0. What we talked about, this corresponds to 1 over s plus a. Therefore, this is 1 over s with a being 0. No computations needed. You can directly use the formula. Now, this is another opportunity to use the exponential function, the Laplace transform of an exponential function, a sine function. It can be sine, actually it can also be cosine. Sine functions, the Laplace transform is omega over s squared plus omega squared. And you can do the definition, do the Laplace integration with f equal to sine omega t and use just the calculus to derive this. But you can also use exponential function pair that we talked about and recognize that, so this is Euler function, Euler formula. So you can also use this important property. Let's use C, x, e j x. Exponential function powered to j times x, j is the index for complex number, is cosine x plus j sine x. This is the Euler formula, very important formula from complex analysis. Because of that, you can say, you can recognize, you can recap from your calculus. If I have negative jx, then it's cosine x negative minus j times sine x. The main point is that sine, cosine functions, they are just nothing but exponential functions in a modified form. You can see if I do addition, then this can cancel out with this. 2 times cosine x is nothing but ejx plus e negative jx divided by 2. Sine, cosine, exponential, same family. From these, you can do, let's do subtraction. This subtract by this. On the left side is e negative ejx minus e negative jx. On the right is 2, so it's j minus negative j, 2j sine x. Sine x is this divided by 2j. We already know how Laplace of exponential function look like. We can directly use that formula. E a t, this is essentially EAT with a being equal to negative j omega. I know EAT, E negative AT is S plus A, so this is S minus j omega. So the Laplace transform of exponential function is this. Therefore, the Laplace transform of sine is, the scaling is going to be the same, but inside I'm going to have Laplace ej omega t minus Laplace e negative j omega t. This is 1 over s minus j omega. And then this is essentially a is j omega. So this is 1 over s plus j omega. From here, you can see when you combine these, you're going to have 1 over 2j, s minus j omega, s plus j omega. It's going to be s plus j omega minus s minus j omega. You can simplify this to generate this. Multiply these two out. You can get s square minus j square omega square. J square is negative 1. So you get negative negative becomes plus. Essentially using some basic properties in complex numbers, then you can get Laplace of sine. This is really important. The Euler formula is really important. Okay? Euler is another fantastic mathematician and engineer. He is a Swiss. He was born from Switzerland. He was born in Switzerland, and he is actually quite a few years later than Newton as well. He spent a lot of time in Germany. He was a professor over there for 25 years. And he has done a lot of things, obviously. This is one of them. But he is also the teacher of Lagrange. I talked about Lagrange earlier. I said there's another story. So Lagrange is Euler's student. And together they worked on, I guess, Euler has very strong mathematical instinct that gives Lagrange very good preparations for his discoveries. Euler, his teacher is also another person that you guys know. He is a student of Bernoulli. Euler is really strong in mathematics. He spent 25 years in Berlin, and then he went back. He is extremely productive scholar. So In his 25 years in Berlin, he generated 350-ish papers in total. So that is, if you calculate it, 15.2-ish papers per month. No, per year. I'm sorry. Yeah. But, so after he goes back, after he left Berlin, in his late years, he is even more productive. He became pretty sick. One of his eye almost got blind, and he did some surgery, and there was some infection. Both of his eyes lost sight almost completely. That didn't stop him. He has really good memories, so he started writing papers just by, he has someone who writes for them, and he does the calculations in his mind. In his late years, when he was even 67, he generates papers 1 per week. 1 article per week, 1 mathematical article per week. Extremely bright mathematician and scholar. All right? Newton, Euler's student Lagrange, and then Laplace related to Lagrange. They are all somehow connected. All right, so I want to give you this formula. It's the same technique that we used. I did sine. You guys can do cosine using the same Euler formula. The key insights to look at is that sine and cosine, they are both second-order term in the denominator. They are both the addition. It's either the addition or subtraction of 2 exponential functions. It's going to be second order in the denominator. The difference is numerator, one has s for cosine, and for sine is omega. Now, impulse functions. This is something that is very interesting. Direct impulse is something that looks like this. It's like a hammer hits a mass, and the mass immediately has a velocity and can move. It's a very fast. Something happens, something very large in magnitude happening in a very short amount of time. That's an impulse. The background, this is not a regular function. This is called a distribution. This is a generalized function. Regular function, the concept of regular function, like if you want to talk about derivative, the general tools for derivative doesn't work. This is a generalized or called distribution functions. So it goes, actually, the background, at least one of the application is as follows. Imagine for step functions that look like this, it jumps from 0 to 1 at time 1. This function is not continuous. It's piecewise continuous. It's continuous in this range when t is less than 0. It's also continuous when t is larger than 0, but it jumps over here. So it doesn't have a derivative at time t equal to 0, strictly speaking, right? But in practice, a lot of cases, we still want to have this concept of taking a derivative of some signal that jumps. So how do we do? This is what we do. We say, I can approximate this step function.
Hello, Professor?
Yes?
Can you unmute the wireless on the podium?
Can you hear me now?
No.
No?
Can you test it again?
Testing.
Okay, it's good.
Okay.
Thank you.
Okay. This is a time varying system. Let's continue here. We say it's good to be able to have a concept at least for derivative of a step function that looks like this. How do we do that? The way we do engineering is that we can do approximation. I can say, I can try to approximate this step function by this. Let me use a different color. I can do approximation that looks like this. It's exactly the same here, and then I'm going to not jump immediately, but have this sort of transient in between to go here. I can make this smaller and smaller. I can move more to the upper left as this time here, let's say this tau, as this tau becomes smaller and smaller, I get a better approximation of a step function. But this new function, I can calculate the derivative in this range. I can calculate the derivative of so this is tau here. There's a smaller tau here, tau tilde. I can calculate the derivative perfectly fine in this range. So over here, it's a slope. It's a constant slope. So its derivative is constant. Let's say somehow it's like this. It has a derivative over here without problem. And then the derivative is 0 once we hit here. When tau becomes smaller and smaller, I still can do derivative. It's just this magnitude going to increase. So as I go to the limit, I approximate the step function better and better by going to the top left. This is having this duration becomes shorter and shorter and then larger and larger in magnitude. In the extreme case, we get this. Effectively, we have a way of calculating the derivative of some function that has a jump. That's how the distribution, the delta impulse, becomes helpful. Take the limit. The limiting case is called a distribution. It's not a regular function. It's an extreme case for something that goes gradually to infinity. All right. Then some common terms that you probably know already, just to recap. Impulse, we don't evaluate it in the usual way, but we look at it, the property from integrals. If you integrate an impulse function, it's like this one, right? I integrate this, the area is the same. And if it's a step impulse, then it's integrating to 1. And then the impulse is sort of like, it can be functioning to pick up some specific values of f at some time. If you integrate delta t minus tau, this impulse here, this impulse hits a continuous time function f, then it creates all these, right? When t is not equal to capital T, it's going to be 0. All the other values are going to be dumped out. So it picks up the value of f at time capital T. So that's the property of this integral. What we want to do is to look at the Laplace transform. This is extremely easy. Laplace transform of a delta impulse, by definition, is integration from 0 to infinity e negative st times delta t, right? What we said in the last page is that delta picks up the value of a function at a specific time. So in this case, the function f is e negative st. It picks up the value of f at time t equal to 0. So you get e negative s times 0 from the derivative. And that is 1. The Laplace transform of impulse is 1. This is something that's very useful and handy. All right. It's worthwhile to remind us that Laplace transform, by definition, this is linear. It has fantastic properties. Superposition works for Laplace transform. By definition, this is integration ft e negative st dt, right? If you swap f with some linear combinations over here, then it's just going to be carried out by superposition. So the Laplace transform of a linear combination of two functions is just going to be the linear combination of the Laplace transform of these two functions. We actually used this property in one of the slides earlier. which slide do you guys, can you guys, yes, the sine function. So in the sine function, I actually use this property sine omega t, right? Sine omega t is a linear combination of the exponential functions. We use this superposition property exactly over there. We computed Laplace transform of this by considering the Laplace of the individual functions here. Super helpful. Two more properties for control system analysis. Integration or derivative. That's very common in actual control system analysis. The Laplace, so it's very important to know this property. What is the Laplace transform of a derivative of a function? So let's say f corresponds to f of s, and then I want to know the Laplace of f dot of t. All right? This is derivative. This is a property of taking derivative in time domain means multiplication by s in Laplace domain. This formula, more formally, it depends also on the initial condition of the function f of 0. So we're going to go through some examples later, but for now, it's very important to build the concept to remind us derivative in time, multiplication by s in Laplace domain, then considering the initial time. You can prove this formally just by integration by parts, which as an exercise you can go through. And we have already done integrations a few times, so the main technique is just going to be applied to here, and I won't repeat them. This goes in hand with the derivative, with the integration. Derivative in time domain is multiplied by s. Then integration in time domain is division by s. So this is coming hand in hand. The opposite of derivative is integration, and then you have multiplication, you have division instead of multiplication. Very useful properties, and I will bring some examples in a few minutes. Any questions so far? So we are here, just two more. Let's see. So two more general properties, and then one analysis tool for control systems. Another property that's really useful is multiplication in time by exponential function. So this is effectively doing, we talked about, I may have a function that goes up or go down, right? This is effectively applying a scaling factor at all time. So this changes the shape of the function at all time. So the scaling is different at different times. This scaling is very easy to express in Laplace domain. So multiplication by exponential function is just a shifting in S domain. E to the power of negative at times ft corresponds to fs plus a in Laplace domain. You already actually have seen this already. So we talked about this one, right? We started by saying the Laplace of exponential function is 1 over s plus a, and for step is 1 over s. You can see this is exactly matching here. I have this function is the step function multiplied by exponential. Is exactly replacing s by s plus a. It works. A useful property is that for sine, just as an exercise, if you want to evaluate a damped version of sinusoidal functions, right? This is damped version of the sine. Then it's just replacing s by s plus a. We talked about multiply by exponential function. And then if you multiply, if your scaling is t, then it's derivative by s. Multiplication by t is differentiation of f of s over s, with negative over here. You can also understand this property used is very handy if you think about Laplace transform pairs that look like this. A step is 1 over s, and then a exponential, it's a linearly grow time function t is 1 over s squared. And then this is related. Essentially, once I know this, I can calculate this using this property. This is, using this property, is negative derivative of s to the power of negative 1 over s. And then this is negative derivative of s over to the power of negative 1 is negative 1 s to the power of negative 2. So it's this one. This is super helpful when your function has scaling factors t inside. All right. Time delay functions, if you shift your index in time domain by tau, then it's multiplication in f. Laplace transform of f t minus tau is e to the power of negative s tau times f of s. There is a large set of problems in control systems. It happens in practice if you think about, I want to control something in a different town in the East Coast. Then all the communications is going to have time delay. So all these problems is going to be involving this exponential function inside. And then there's a large set of algorithms just trying to make the impact minimum. All right. So as you get to use these properties more, then these relationships is going to be pretty handy in your mind. So one of the things that is key for ordinary differential equation is this property. Is the property of, if you have integration of this sort, it's convolution. If you have a signal f going through some multiplication convolution with another signal g defined in this form, then the Laplace transform is amazingly simple. Something that looks complicated in time domain is extremely easy in Laplace domain. That's the property of convolution. I'll give you one example over here. You all know that if you define here the Laplace transform between g and capital G like this. So if you say the transfer function g is the Laplace transform of little g, here g is the impulse response of the transfer function, right? So that's the property how it's defined. If you apply impulse to a transfer function g, you get a time sequence, and that time sequence is defined as the impulse response of g. Now, we talked about the impulse response is Laplace transform is 1, right? The simplest Laplace transform over here. You can see then because of this property over here, if you think about what does it mean, like g is the impulse of this, is the impulse response of capital G. How is defined like this? Why is the impulse response of capital G is the inverse Laplace transform of the transfer function? is immediately relevant from this picture. Because in the Laplace domain, an impulse is 1. You apply an input to a transfer function, you get an output. In the Laplace domain, is what? It's just multiplication. So in the Laplace domain, the output, when you apply an impulse to a transfer function, in the Laplace domain, the output is g. It's the transfer function itself. This is the impulse response in the Laplace domain. That is why, if you go to the time domain, this little g is the inverse Laplace transform of capital G. That's how it's defined. We're going to use this concept in another example related to the final values theorem. So, two important theorems for Laplace. You can go from time domain to Laplace domain like this. You can know the initial condition of a function by calculating the Laplace transform and then multiply that Laplace transform by S and then evaluate that function by letting S go to infinity. Laplace transform, this property relates to the functions in time domain and in Laplace domain. It relates to two specific values of the functions. I can find out what will happen to the function at specific time instances by going to look at it just from the Laplace domain. This is the result. I will read this result first to you. F function at time 0, this is 0 positive, is whatever when, if it's a moving mass system, if I'm considering Laplace transform, if I'm considering motion of a mass, let's say here, there may be some springs and dampers. This is 0 plus, means scenarios that look like this. I apply a hammer, I apply a shock to the mass. I can know immediately what is the velocity of the mass after the shock by looking at the Laplace transform combination of S times Fs. Okay, so 0 plus. So this is the first time that we talk about, we really distinguish the difference of time. Okay, so it's something that happens very rapidly after a shock, let's say, at time t. This is almost analogous to the other property, the final value theorem. Initial value theorem tells you what happens for the function at time t 0. Final value theorem tells you what happens eventually in the end. And they are just evaluating the same term by letting S go to different values. One go to infinity, so you want to know initial condition, go to the infinity in the Laplace domain. If you want to know what happens eventually, let Laplace domain property go to 0. This goes in very handy. The proof of these formulas mainly go from the definition. And you can get the proof of these very easily by going to the internet. What I want to emphasize is when to use these guys. This property doesn't hold all the time. It has a distinct assumption that must be satisfied. And that assumption is this must exist. If the function at infinity doesn't exist, it's not a constant, then it doesn't make sense to go to this step even. Right? As an example, try, if I do final value theorem on this y1 infinity, so limit y1t. If I use the final value directly, this is going to give me limit s go to 0, s times 3, s plus 2, s squared plus 2s plus 10. S is going to cancel out. And then the remaining terms, I can simply let s go to 0 and get 3 times 2 over 0 plus 0 plus 10. So that's 3 over 5. This is what the final value theorem tells me about this function value y1 at time infinity. Now, if you do this over here, you do the final value theorem, let's see what we can get. y2t. So it's going to be 3s over 3 minus 2. Right? What would be the value from here? 0. But however, what is the time domain function for this Laplace transform? So we talked about 1 over s plus a corresponds to e negative 8t. This is 3 times 1 over s minus 2. So it's 3 times e. A is negative 2 in this case. So this is e2t. This, it looks like, so it's 1, 2, 3, and then goes up. So you see the issue here. This function, this time function, it is infinity when t goes to infinity. But the final value theorem doesn't tell me that, because this pre-assumption is not satisfied for this case. You all know that this transfer function, the pole is at 2, right? So the pole of this transfer function is on the right-hand plane. It's unstable, the system. So that's why you cannot use final value theorem for this problem over here. All right. Let's take a look at some of the most common Laplace transform pairs. It's worthwhile to take a look at them and see some of the connections. So we see the connection of from impulse to step and then to exponential functions. These are all connected. And then from a step function to a time t function, its derivative property. So it's 1 over s becomes 1 over s squared. As this is essentially going, your input function, your f, is becoming 1 order more complex with t involved. And if t is to the power of 2, this is another order of complexity added to the function. Then you get s to the power of 3 in the denominator. Then some other things we saw, sine, cosine, and then exponential damped sine, cosine. These are all using the basic properties that we saw. Next time, we'll talk about some applications of these Laplace transforms.